Okay, good morning, everybody. So let us continue our discussion of clustering. So we stopped here yesterday. So we said, for example, you can convert a data set into a graph and then transform the problem of clustering a data set into the problem of graph partitioning. So we said if you take the entire distance matrix or proximity matrix of the data set, right, you can map that onto the adjacency matrix of the graph. So then the clustering problem becomes graph partition problem. That is, how do you graph?
Okay, sir. Okay.
Sorry. Hello. Yeah. How do you cut the graph so that the number of edges that you cut, right, is minimum? Okay. So the thing is, when you do clustering, the characteristics of the input data are important. So these are some of the important features that you will consider, right? So, for example, the type of the proximity or measure, density measure, right? It is one important feature. Then there is sparseness. If the data is sparse, that is, if the vectors are sparse, right, that decides what kind of similarity you have to use. You remember when we said if the data is sparse, you may want to use Jacquard distance or Jacquard similarity and not Hamming distance. Right, so that kind of choice also improves efficiency of calculation. Then attribute type again is a very similar thing. It dictates type of similarity. Suppose the attributes are just qualitative attributes. So then you will just match them, and if the match is there, it is 1, otherwise 0. So that's the kind of similarity that you would do. Your attribute type also determines the similarity. Then the type of the data also dictates the type of similarity. Then dimensionality, if it is high, then you have to worry about that. You want to come up with ways of reducing the dimensionality. Then noise and outliers, you have to watch out for them. There are ways of finding them and eliminating them or removing them from clustering process. Because if noise or outliers are present, then it will mess up your clustering. You will get either very small clusters or you will get empty clusters and things like that. We'll discuss that as we go along, etc. Okay, so there are three types of clustering algorithms which we'll be discussing in this course. Under each of them, there are several examples. The first one, most important one in a pretty large family of algorithms, is the prototype-based clustering, right? And then you have graph-based clustering and density-based clustering. We have just outlined, kind of what these ideas would look like, right, before in the last class. But from now on, we'll go through each of them and discuss them in detail. So in prototype-based clustering, like I was mentioning yesterday, each cluster is represented by a prototype or a representative point, which is usually called a centroid. So in this example, you can see that there are two clusters, and each cluster has a representative point. So for example, this red dot here represents the entire data set. This blue dot here represents this entire data set. So all the points for which the red dot is the closer centroid, right? For example, for all these points, this is closer than the blue dot. So all these points form one cluster. Similarly, all the blue circles form another cluster. Now, not only these dots, the data point, which are data points, you can divide the entire space into partitions with the help of the centroid. For example, instead of just the dots, if you say take any point in the plane, right, which of these centroids is closer to it? Is it this one or is it this one? Depending upon that, you can label every point in the plane and put it in either cluster 1 or cluster 2. So if you do that, can somebody tell me how will you divide the plane? How will you end up dividing the plane with two clusters? By that criterion, that is, I take any point in the plane. I ask which is closer, the centroid 1 or centroid 2. If it is centroid 1, I put that dot in cluster 1. So if you do that, how do you end up dividing the plane? Any suggestions?
Plane perpendicular to line joining those two clusters.
Plane perpendicular or something else?
Perpendicular bisector, actually.
Yeah, perpendicular bisector. Take the line joining the two cluster centers, that is centroids, and draw a perpendicular bisector. Right, that bisector divides the plane into two halves. Right, so you can say that this entire half belongs to cluster 1, and this entire half belongs to cluster 2. Okay, so same thing we'll be doing in n dimensions when you have more centroids. Okay, that's the most general case. So the prototype-based clustering not only lets you cluster the data points present, but also lets you cluster or partition the entire inputs to the data space, right, into partitions like this. Okay, let us look at the first one, the k-means clustering, the famous, right, one of the most popular and commonly used clustering algorithm. It has some problems, but this is the first thing that people generally learn. So this is based on partitional clustering approach. That is, it's a flat structure. That is, you just divide all data sets into some k partitions or k clusters. And this is a prototype-based clustering algorithm. So each cluster is associated with a centroid. Then each point is assigned to the cluster with the closest centroid. So if we have a bunch of points, I'll see some examples later. We have a bunch of points and a bunch of clusters. For every bunch of points and let's say a bunch of centroids. For every data point, you see which is the nearest centroid, and then allocate that point to that centroid. So like that, you divide the entire data set into clusters. And if you want to divide data set into k clusters, you have to specify it. So sometimes what happens is, suppose I have data like this, a toy example. You can see that there are two clusters. But when you give this data set to k-means clustering algorithm, you can't say, hey, just give me the clusters in the data set. The algorithm will ask you, how many clusters do you want? Right? It doesn't know that there are intrinsically two clusters in this data set. You have to specify. If you say, give me 10 clusters, it will divide this into 10 into subsets and give you. Right? The algorithm itself doesn't decide how many clusters are there. You have to specify. There are other algorithms which do that, which can say that, okay, by a certain criteria, I think that there are some 20 clusters in this data set, and these are the 20 clusters. Some algorithms give you that. So the basic algorithm is quite simple. So let's say you have some n points, totally n points, and then I want to divide it into k clusters. All right. So how do you do that? You randomly take k points, and in fact you select from the data set itself, select from this n k points from this n points, and initialize them as the centroids of the k clusters. Then once you do that, you can allocate data points to the clusters, to the centroids, by this nearest neighbor criterion, right? That is, as take any given point, see which of the centroids is closest to it, and allocate to that. So like that, you can divide data set into k clusters. So that is the first step. Form k clusters by assigning all points to the closest centroid. Then, then what happens is, once you form the centroids, so the centroid, like I said, is supposed to be the center of the cluster. That is, its average of all data points. So now, if you allocate if you allocate the points to centroids like this, then once you form the cluster, it is not necessary that the centroid is the average of all these points. It's not necessary. So then what you do is you take average of all these points and move the centroid to the actual average of the cluster. Now when the centroid moves, the allocation of points will again may change, because now that the centroid has moved, then if you ask, okay, is for a given point here, for a given point here, is this the closer one or is this the closer one? So that equation might change. So then, because centroid has changed, you will reallocate the points to centroids, right? And once you reallocate, your clusters change. Once clusters change, again your centroids will have to be recomputed, because centroid is always the average of the data points in a given cluster. So what happens is these two keep changing together, one changing the other, right? This goes on for some iterations. After some time, you will reach an equilibrium state, a steady state. Your clusters won't change any further, and therefore your centroids also don't change any further. When you reach that state, the centroids don't change anymore, right? You stop this iteration. So the final clusters that you get are the solution, right, of the clustering algorithm. So let us spend more time on this and discuss this. So initial centroids are chosen randomly by simply selecting from the given data set, right? And another thing is the actual clusters that you get might depend upon your initial condition. This is one problem with the k-means, but anyway, that's a property of k-means. A centroid is typically it's usually the mean of the points in the cluster. So that is what we do in this course also. And the distance measure that you use, we typically use Euclidean distance, most convenient, right? And you can also use similarity measures like cosine and correlation, etc. So there are theorems which say that k-means will converge for common similarity measures. But if you take any of these things, these distance or similarity measures, k-means process will converge for a given data set. So that is guaranteed. And most of the convergence happens in the first few iterations. After that, there will be only small changes. A few clusters keep changing for a little while before they also settle down. Okay, so the complexity of this process is given as Ki and D. What is Ki and D? N is the number of points, K is the number of clusters, I is the number of iterations, and D is the number of attributes, that's the dimension. So how does this work? Let us say this. So let us say these are the data points. I'm just drawing data points, okay, like as if they're all on one side. So there are n of them, n points. And then I'm denoting the clusters on the other side as if they're all separate. This is just to explain this computation. Okay, this is points are all obviously mixed up. So what you do is for every data point among this n, you have to calculate distance of this to each of the k centroids and find out which is closest, right? So how does that work? You do so if x is the data point, and so x is the data point xi, mj is the centroid, then xi minus mj this thing square, that is what you have to calculate, right? And so how many computations are involved in this? Each of this distance calculation involves, right, d computations, because d is the dimension. So this square has n d terms in it. So there are d computations. The d computations of some difference calculation and square. Okay, that is what I mean by one computation. Now you do those d computations for each of the data points and each of the k centroids. So you'll end up with the d times, d times n times k. Now this computation you have to do over and over for n iterations. So times, I iterations. So that is d times n times k times n. So that is how that gives you the complexity of this process. So let us see how this kind of a clustering works with an illustration. Now this is a data set. Ideally you can see that this is a toy picture. I mean, a lot of these pedagogical examples which you see in textbooks are just are very nice to explain concepts and all that. But in real world, when you have huge dimension, a lot of data, you don't know what the hell is going on, right? So you have some measures by which you can find out, did the number of clusters that we got, is it the right number, things like that. But you cannot visualize and tell stories. So this is only for paper writing and giving illustrations in giving pedagogical illustrations. Okay, so if you see this picture, you can see that there are three clusters in it, and so that is your optimal clustering. So let us see what the algorithm actually gives you. If you find something like this, then that is suboptimal. That is, this can happen. That is, I want to divide this into three clusters. Right, the algorithm actually gave me three clusters, but look at the clusters. This blue is one cluster, this light green is another cluster, and the entire brown is another cluster. So this is possible. The algorithm can do something like this. It depends upon initial clusters, initial centroids. Now, when we do this process, when we follow this algorithm, right, this is the k-means clustering algorithm. What you're actually doing is minimizing this objective function. Okay, so what is objective function? Uh, for every point x, the error it is the distance to the nearest cluster. So mi, right? You assume that is always the distance to the nearest cluster, right? And then you add this up over the entire data set. That is your sum squared error. X is the data point in cluster Ci, right? And mi is the representative point for that cluster. So if you have let's say three clusters, there are some points here, some points here, some points here. So for all these data points, calculate the distance to its centroid distance and do the sum of distance squared. Then similarly for all these data points, do the sum of distance squared to this centroid, and similarly do it for this. Now add up all these three errors, right? So that quantity is called the sum squared error, and this is what will be minimized when you do this iteration of the k-means clustering algorithm. And how is it meaningful? Because what are you doing when you're doing this? You are trying to make sure that the distance of all the data points within a given cluster is minimal. Because you are consciously trying to minimize that cost function. Now, how does it tie in with our original definition of clusters? A cluster is something where the intra-cluster distances are small and inter-cluster distances are large. In k-means clustering, what are we doing? We are trying to consciously minimize intra-cluster distance. Even that we are doing in a special way. So inter-cluster distance would be ideally have a bunch of points like this. I have to consider every possible pair of distances, right? And then try to minimize, make sure that that is small in some sense. But we're not doing that. We are taking an average value, right, or some kind of a centroid which is representative of the entire data set, and we are trying to just minimize the cost, the sum of squared distance, right, of this to this value. And so, okay, that is this. That is what we are minimizing in this case. Now, and we can show that mi corresponds to the center of the cluster. So you know this result, right? Let me. Okay, so let me just show one small thing. So you know that let's say I have some data points in 1D, okay, xi, which is all in real numbers. Now, so these are all data points in one dimensions. I want to pick a point among them so that it acts like a centroid. And how do I do that? I look at this quantity, xi minus m whole square. I goes from 1 to n. That is my cost function. So what is the value of m which minimizes cost function? Can somebody tell me? Anybody? So how do you do that? M such that E is minimum. Okay, so what is this? What is that M? So how do you do that? Find out dE by dm. Okay, is equal to half of sigma I equal to 1 to n xi minus m is equal. This should be equal to 0. Right, so I can ditch this half, I can ignore that half. So sigma xi is equal to sigma m up to n. So what is this? Now this is equal to n times m. This is equal to summation. So if you remove this and bring one n here. So what's the moral of the story? What do we learn from this? Right, the representative value of m, which minimizes this entire cost function, is nothing but the average of all these values. So this is a property of one of the properties of the average. Right? If I have a bunch of numbers xi, then if I define a cos so that from every point I look at the difference, square it, and take the sum of all those errors, right? And that quantity is minimized when that point is actually equal to the minimum of all these points. You can show the exact same thing when xi is in Rn. So then we'll use different notation. We'll use capital N here. Capital N, capital N. Okay, you can do this as a homework problem, right? So you can do is equal to sigma I equal to 1, then so xi minus, now m is also a vector. Okay, so minimizing E would mean del of E with respect to m. So again, you'll get the same thing. So you will get m is equal to sigma xi I goes to 1 to n. So this is and 1 by n. We'll get the same result even for n dimensions. So what we learn from this is when you have a bunch of points in n dimensions, if I want to pick a point such that the sum of squares of all these distances is minimum, then pick that point to be equal to the average of all those points. So for that, okay. So this is actually the idea behind, key idea behind K-means clustering algorithm. So whenever you have a cluster, right, you reset the centroid to be equal to the average of all the points in the cluster. And why do we do that? Because when you do that, this cost becomes minimum. And why are we minimizing that cost? Because this is one way to realize the intuitive idea behind clustering. Right? In clusters, a good clustering is one way. Then intra-cluster distance is minimum, and inter-cluster distance is maximum, right? In K-means, you are only focusing the intra-cluster distance, right? And so the idea is that if the distances within the cluster are small, automatically distances from other clusters will be large, right? Because both are opposite. So this is the idea behind this whole algorithm. Now, like I was saying before, the K-means partitions the input space using nearest neighbor criterion. That means if I have two centroids like this, so this is number 1, this is number 2, and I want to divide every point in the plane uh, by in terms of the nearest neighbor criteria. That is, which of the centroids is closer. Okay, so then if one is closer, I put it in cluster 1. So if you do that, I can divide the whole plane or whole input space into K partitions. So that will be simply this kind of a perpendicular bisector I was saying before. So if the centroids are like this, then the bisection will be like this. So it's simple. So there's a nice geometric problem associated with with clustering. Now it gets more tricky when you go to more centroids. If you have 3 centroids, the blue dots, right? Then the partitions will be like this, or the boundaries will be you take this, connect these two, and take this line. Draw a perpendicular bisector. Take these two. Draw a perpendicular bisector. Take these two. Draw a perpendicular bisector. And from your high school geometry, you can show that these 3 perpendicular bisectors, right, are concurrent, right? So they intersect at a point. Now, so these are the borders, right? Now we have successfully divided the plane into 3 partitions. So this whole thing is one partition. Of course, this is going to infinity. Okay, I'm just drawing it just to indicate. This whole thing is another partition, and this whole thing is another partition. So this is how the partitions look when you have 3 points. In general, if you have a large number of Ks, right, partitions look like this. So you see that the red dots are all the centroids, and so if you have divided the plane into small polygons, and you see the polygons are all convex, right? You don't see any concave polygons. You don't see anything like right, Right? We don't see anything like this. Okay. What else? So you see that everywhere what we are doing is you connect to neighboring dots, neighboring centroids, draw the perpendicular bisector, neighboring dots, perpendicular bisector, and they all intersect. Right? They are always concurrent. So divide the whole plane into a bunch of polygons, uh, convex polygons, and some polygons are finite, some are infinite because the ones close to the border, right? They'll open up into the plane and they're infinite. Now same, so this is how it looks. Again, just a colored picture of the same thing. Now same thing you can do in multi-dimensional space, more than 2 dimensions. Then you divide the whole space, the 3D space or ND space, into polyhedra. 3D space, you divide this into polyhedra. See, one thing you can notice here is all the partitions have straight lines as borders. You don't have like curved partitions, right? Now, similarly, if you go to 3 dimensions, all the partitions will be polyhedra. Each of them is a polyhedron. And if you go to my n dimensions, obviously you cannot draw, right? You will have some kind of a hyperpolyhedra, right? So that's how you divide the entire space, right? Each of these polyhedra is like one cluster. Each cluster is contained inside one of these polyhedra. Any questions on what we discussed so far? Just tell me if you're going too fast or too slow, whatever. Okay, so like I was saying, when you do this clustering iteration, you are basically minimizing some cost function. Okay, and this cost function does not typically have a unique minimum. There have lots of minima. So which minimum you land, right, depends upon your initial condition. So your cost function, we called it SSE, right, sum of squared system. So this depends upon your some MI. MI are the centroids. So think of this SSE as having lots of minima. Now you are moving your MI so that you land in a minimum, right? Since you have lots of minima, depending upon the initial condition, you can land in any of the minimums. If I start from here, I'll roll down and land. If I start from here, roll down and start from here, roll down. So because of this, there is no unique solution, and depending upon initial condition, you might land in some solution or other. So if your initial solution is good, then you have a higher chance of landing in a good final solution. So take this example. The initial plus centroids are like this. So these plus signs are the centroids. So you start from there, start the iteration. Okay, the centroids are moving, right, and pluses are also changing, right. So after iteration 5, these are the 3 centroids, one here, one here, one here, and the pluses are also pretty decent. Okay, so you saw that. So almost it has caught the 3 main clusters in this data set, this one, and this one. And the K-means clustering has found them. So same thing we are seeing as a bunch of snapshots. So initially the centroids are here. So the clusters are like this, right? The blues are one cluster, greens another cluster, browns are small cluster. And after a few iterations, right, it's able to find the proper clusters. But take a different kind of initialization. Initial ones are here, here, and here. Initial centroids. So you go through that a little bit. So what happened? So these are the final centroids after 5th iteration. With only running for 5 iterations because probably it has converged by 5 iterations. So you have the first one is here, and around this, if you cluster data points, you get one cluster. This is the green cluster, and second centroid is here, and that's your blue cluster. And the third centroid is here, right? It is neither here nor here, but somewhere in middle. This no man's zone, and all these points, right, are now grouped around this third centroid. So it really messed up because what was one cluster, it actually divided into 2 clusters. and what were two clusters, it merged into one cluster. So it gave three clusters because we asked for three clusters, and kind of we know that there are supposed to be three clusters, but the clusters it gave are the wrong ones. Okay, and it will turn out that if we actually calculate the SSC, right, and for this configuration of the centroids, it will turn out that it is a local minimum. It is a minimum in a relative sense. That if we just take small deviations from this and calculate SSC, that SSC will be slightly higher. It is a minimum, but it's a local minimum, right? Whereas this one, the other one which we saw before, this will more likely be a much smaller minimum. Okay, but we missed that because of the bad choice of initial centroids. The same thing is shown as a bunch of snapshots. So we see that this problem of selecting initial centroids is quite a crucial problem. And there's no simple way out because the whole problem is we don't know what the real clusters are. So we cannot just choose from. So it would be great if we can somehow choose each centroid from one cluster. So that means we already should know the answer, which is obviously not possible. But let us look at the probability of choosing centroids like that. That is, if the data set has k partitions, right? Now let's say I'll just draw it more conceptually like this. Right, let us say the data set actually has only 4 clusters, right? And the best way to take ideal way, if I have the choice, is to take 1 point from here, 1 point from here, 1 point from here, 1 point from here. Any of these things will do, but I'll take one of them. I cannot take 2 from the same cluster and none from something else. So that's what we have done before, and that gave bad results. So to select centroids like that, if I randomly select k centroids from the entire data set, what is the probability that each of these centroids come from one and only one of the clusters? So how do we calculate that? Assume that the data set can be divided into n small n clusters, so it means they're of the same size. So the total data set, total data set size is equal to k times n. Okay, so if you do that, what is the probability of selecting the centroid such that I select only one centroid from each cluster? So within each cluster there are small n points, right? So I can take those points in n different ways, and I can from this also I can take data points in a centroid from in n different ways. Here also in different ways. So the number of ways in which I can select one each, right, from each of the clusters is n times n times n times n, etc. K times. So that is n power k. Now the order in which I select, right, doesn't matter, right, because I just want one centroid to be taken from one cluster, but I don't care which order to select from. That multiplied by k means, sorry, k factorial. So k factorial times n power k, that is the total number of ways in which I can select centroids such that I take one centroid per cluster. It looks like a large number, but if you look at the total number of possibilities, that is the total data set size is kn. I just have to select k points from that. So and then I can reselect the same point, right? Assume that make the calculation simple. That's all. So that will be kn times kn times kn times kn times kn. You do it k times. Right, so that will be kn power of k. So numerator is k factorial times n power k, denominator is kn power k. So if you cancel off this n power k, so you get k factorial by k power k. This is a very small number. This number decreases very rapidly as you increase k. So note that it doesn't depend upon n, it doesn't depends only on k, the cluster number. So if k equal to 10, this number becomes 10 factorial by 10 power 10, that is 0.00036. So basically, it's bad news. It's what it is saying is the probability of selecting centroids initially by an ideal way is pretty small. So you just hope your luck favors you and get a good set of initial clusters. So let us see how it works in case of 10 clusters. Here in this again a toy data set which has 10 clusters. The initial centroids are shown here. All these plus signs are the initial centroids. And if you cluster the data set based on these initial centroids, it's pretty bad. As you can see this. These are all the each cluster is shown in one color. Okay, so all the yellows are one cluster. So that means what is two clusters is now merged into one cluster. And these blues here are supposed to be part of this cluster, but they are split separately because there are two centroids here. In the same sense cluster, there are two centroids. And in this cluster, there are no centroids at all. So unfortunately, it's a bad kind of clustering. But let us see what happens if you run this with k-means. Not bad, right? So we still got good clusters. So the thing is, although that is ideal situation where you take one cluster from one centroid from every cluster initially, even if you don't do that, sometimes k-means can just tide over it and give you a good final result. But that's the ideal thing. If you do that, you'll definitely get a good clustering. But even if you don't do that, sometimes you might luck out and get a good final clustering. So the same thing is shown here, right? But it may not be you may not be always that lucky. Look at this example, right? Slightly differently chosen centroids. Okay, and initial centroids are obviously not very good. But if you run this, so it settled very quickly and settled at a bad clustering. You see that this is 1, 2, there's a change, 3, very little change, 4, same thing. And what happened? First two clusters are okay. The 3 and 4 actually got merged. So the centroid here sitting between two clusters. Then 5, 6 again are okay. 6, 7 are okay. 7, 8 are okay. 9, 10. Actually, there are two clusters, but there are three centroids here. So one of these clusters got split into two clusters. So these two clusters got merged into one large cluster. And this cluster, which is only one cluster, got split into two clusters. Okay, other than that, everything else is okay. So anyway, so this is how the choice of initial centroids will affect your final clustering. And this is a fundamental problem. There is no simple way out. There are some hacks to improve the situation, but there is nothing like a perfect solution where this problem will never arise. So there are ways to just tide over this problem and try to minimize the probability of ending up with a bad set of clusters. So basically what you do is try multiple times. I mean, this is a commonsensical thing. If you fail exam once, you write the exam again. That's something like that. So you do multiple runs, but again, the probability is not on your side. So again, you may or may not get a good set of clusters. Then how do you choose what is the best one? Based on the SSC, right? You try the clustering multiple times, and you choose the clustering that you get, which has the smallest SSC. Now sample and use hierarchical clustering to determine initial centroids. So you do some hierarchical clustering, right, and then use the result of that to determine initial centroids, and then do the k-means clustering. So okay, it sounds good, but point is there's obviously a lot more computation because this itself is quite computationally quite expensive. Then select more than k initial centroids, and then select among these initial centroids. Among them, you see which are the centroids which are bad in the sense the centroid. Say ideally, if you cluster the data set into k clusters, all the clusters should have ideally about the same size. Right? If you have some clusters which are very large, some clusters which are very small, then that's not a good way of dividing it. So, what they are saying is you take a lot of centroids, and at the end, if you have very small centroids, remove them and recluster them, right? And if you have very large centroids also, then you put more. If you have very large clusters, you put more centroids there and break them. Okay, so then you also do some post processing. So, for example, sometimes when you do clustering, you might end up with empty clusters. That means there is a centroid there, but there are no data points in it. What's the point if, sorry, pardon my pun, but what's the point if you, right, if you have a cluster centroid, but there are no points in it? Okay, bisecting k-means. So this is an interesting way of, solving the problem, of addressing the problem. So we'll come to the bisecting k-means in a minute. Now there is also the problem of empty clusters. That is, some centroids might have not have any points, right? So that is, and this bisecting k-means, the k-means algorithm can give you empty clusters. So how do you, like I said, choose a point on the cluster with the highest centroid, and the empty clusters, then you remove those centroids. So here is an illustration that shows how you can end up with empty clusters. So these are the points in this data set. It's a very tiny toy data set. 1, 2, 3, 4, 5, 6, 7. There are 7 points, right? And okay, so initially I've taken 3 centroids. See that centroids are given as plus signs, shown as plus signs. One here, and one here. So so for the initial location, right? Okay, so I've taken 3 centroids. So points 3, 5, and 6 are chosen as our initial cluster centers, because your initial centroids have to be chosen from the data set itself. That is, I mean, that's a good practice. So we have done that. And when you do that, and for then you allocate the points to the centroid. That is, for every point you see which is the nearest one. So for 2, 3 is the nearest one, closer than 5 and 6. So put with this. For 1, same thing. 7, same thing. Okay, you do that. Now, so when you do that and recalculate the clusters, right, it turns out that 3, 2, 1, 7, these 4 points form one cluster, and their average, right, is the new centroid comes here. Initially, this centroid was at 3. After doing one round, this centroid moved to some point here in between, because the centroid location need not coincide with any of the data points. Only initially it happens because you have chosen them like that. But after a few iterations, since you are taking average of bunch of points, that average may not be equal to any of those points. It can be out there in the right. So that's what is happening here. And for 4 and 5 become one cluster, and the average of them is this. 6 happens to be a singleton cluster. That is, there's only one point in it. That's the centroid. So do that once more. Right now, 4, which was part of this blue cluster, now merged with joined this red cluster. Okay, and then 5, which is part of the blue cluster, now joined this green cluster. Right, and once that happens, this fellow is now left stranded without any data points. There's only the centroid, but there are no data points, because we are doing clustering for the data point, not for centroids. Centroids are just some kind of reference points, right? So this is one example of how you can get empty clusters. Okay, so there are few more things to discuss, but I don't want to rush. Right? Any doubts? Does anybody have any doubts? We'll do a tutorial on this maybe the coming Friday, so that you can actually try your hand at this k-means clustering algorithm and see what happens. But I think we'll go a bit slow. And do you have any questions?
Sir, I have a question.
Yeah.
So you mentioned that when you're using multiple runs, it's not like a good strategy because probability is not on your side. Is it possible to do multiple runs and consider optimal local clusterings?
Yeah. So that's what. So when you do multiple runs, okay, probability is not on your side, but the only way to pick the best among them is for every clustering you will have an SSC, right? So if you do this 10 times and pick the clustering which gives you the lowest SSC, that might be reasonable.
No, so yeah, but again, that is difficult because you're unlikely to pick very good initial centroids. Instead of like an overall SSC, is it possible to consider local SSCs?
Yeah, so those are the kinds of things we'll do in case of this what is it called? Bisecting k-means. See that?
Okay.
Yeah, we'll discuss that in the next class tomorrow. Not tomorrow. Yeah, next class, next Monday.
Thank you, sir.
Any other questions? So basic idea, intuitive idea behind this is avoid very large clusters, avoid very small clusters. Right. So that's how you get an overall small SSC. Any other questions? Okay, so see you next class.